Alright, we are recording a problem for the wheelbarrow going over a curb. Pretty classic problem, almost as classic as the ladder type problems for statics. It's actually a type where we're looking for exiting the condition of statics. So we're going to be right at that point where we just start to lift off. Okay. We're going to need a really big drawing for the wheel, and we'll probably actually duplicate it. So before I forget, I'm going to make a copy of this. Control C, and then I'll Control V this later. All right, let me show you the question statement. It's not quite square. Control C again. Better. All right, so here is, I hope, the question. Ah, darn. This statics and elasticity. There we go. John is pushing his daughter Rachel in a wheelbarrow when it is stopped by a brick that is 8 centimeters high. All right, so we know the height of this is going to be 8.00 centimeters. I'll copy that off to the side. The handles make an angle theta with the horizontal and 15 degrees. So 15 degrees with horizontal. Alright, due to the weight of Rachel and the wheelbarrow, a downward force of 400 newtons is exerted at the center of the wheel, which has a radius of 20 centimeters. We'll call that an FG, a gravitational force. It's strictly speaking not, but it will do fine to treat it that way. And the wheel has a radius of 20 centimeters, so I'll call that 0.200 meters right off the bat, get everything in the same units. Actually, no, I shouldn't. I'm going to leave this as 20 centimeters. I think it's always going to come out as a ratio, so we're not going to care about the units in the end. Okay. Let's see, part A. Find the force due to John. Part B. Find the normal due to the brick. At the moment it begins to rise up over the brick in terms of magnitude and direction, I believe. Yes. Write that a little more neatly. All right, we've got the setup. In both parts, assume the brick remains fixed and does not slide along the ground. Also assume the force applied by John is directed exactly towards the center of the wheel. That's important. It makes our lives a whole lot easier. All right, let's come back over to what I've drawn out related to the problem. Here's what we've got. We do know the radius of the wheel will be coming along here. That's good. Now we need to decorate this with forces. First thing, there is no normal force equals 0. At the moment, it begins to lift. So just as it starts to go over top of this, we're going to have that normal going to 0. We do still have normal forces here. We've got a vertical component in y and a horizontal component in x due to the brick. We'll use the in x and in y eventually to figure out the magnitude and the direction. We also have the 400 newtons that I was calling an FG. And then we have the fun one. We have the force due to John. So here is the horizontal direction. It is going to be 15 degrees underneath. It is going to be theta, and that is F John. All right. So let's do the easy part first. Sum of forces in x. Force of John, cosine theta, acts in the positive x, minus nx acts in the negative. That'll be 0. Then we have a vertical in y minus Fg minus force due to John sine of theta, and that's 2 of them. All right, let's see. Do we have enough information to go at anything? We don't know in x, we don't know in y, we don't know f John, so we are stuck at this point. We are going to need the third equation for the sum of torques. And this is where things start to get interesting. So first we need to pick a center of rotation. And we're going to pick that center of rotation right at the junction point with the brick, because we don't know either of those forces. So it would be lovely if we can get rid of them, because if we get rid of both of them, we should be able to find torque for Fg and torque for John, force due to John, and that's going to let us figure out the force of John. That'll let us figure out part A. All right, so as far as torque goes, we're either going to think about R times F times sine of V, or we're going to think about R perpendicular times the force, or we are going to think about magnitude of R times the perpendicular component of the force. For one of these, R perpendicular is easy to see. If we look at this and drop the vertical, we can write an R perpendicular that comes directly along here and gets to Fg. That works great. So we'll be using that one for our Fg. For John, we're actually better off going for this. So R will come out directly to the point of application of the force, and then it's going to have to turn. And we either want this outside angle as R phi, or we want the inside angle as phi. I'm going to erase and move the R for radius, so it's not quite so close to the phi. All right. This looks tricky, and we're actually going to do it by grabbing our second drawing. Here's a copy. And we're just going to handle geometry in this. So here, we know this is the radius R. Over here, pull that out. We know this is the height h. That means this part is R minus h. That means we can actually find this part as R squared is equal to R minus h squared plus x squared. That will let us find our R perpendicular for Fg. That turns out to be pretty easy to find. We've got 20 centimeters squared equal to 20 minus 8 is 12 centimeters squared plus x squared. Rearrange that. We have 400 centimeters squared minus 144 centimeters squared, which turns out to be 256 centimeters squared. So that means x is 16 centimeters. So we'll label this R perpendicular is x, and we now know what that is. All right, so let's start to set up the torque equation before we go further. So sum of torques is going to be equal to the gravitation one. We come out, we turn towards it, it gives the thumb towards us, so it's a positive torque. So we're going to get x times Fg. We're going to have to go the other way. It's going to be negative for force of John. So we have R times F John sine of phi. And that will be equal to 0. All right, let's figure out what phi is. So we've got all the sides. We want to find this angle. Let's call it, I don't know, let's call it alpha. Alpha is not great for a rotation problem. We'll call it alpha anyway. Actually, maybe psi would be a better choice. All right, why do we care about that? Well, if we carry this along here, we know that the whole swing, if I go around from here to there, that is 90 degrees. If we think about force of John, it comes out along here where this is theta, so that's theta degrees. So if we want our phi, it goes in the middle there. So psi plus phi plus theta is equal to 90 degrees. which means phi will be 90 degrees minus theta, which is 15 degrees, minus our psi. And we do have enough to do trigonometry here. So we can do inverse tangent, for instance. That would be inverse tangent of x divided by r minus h, which is going to be 16 over 12. So our angle will be 90 degrees minus 15 degrees minus the inverse tangent of 16 over 12. Let's grab a calculator. So 90 minus 15 minus the inverse tangent of 16/12 is 21.87 degrees. We'll keep an extra digit here. We've got everything we need, so looking at our torque, XFG is equal to RF John sine of phi. So force of John is equal to XFG over R sine phi. We get, let me see, X was 16 centimeters times 400 newtons divided by 20 centimeters sine of 21.87. 16 times 400 divided by 20 divided by sine of 21.87 is 859 newtons. So roughly 860 newtons. Okay, we've got that. Now, here's what we're going to do with it. I'm going to make a copy of these two equations. And now we know that is 859 newtons. Okay, so the nx component is going to be F John cosine of 15 degrees. So 859 times cosine 15 is 856.96 newtons. Ny is going to be Fg plus force John sine of theta, or sine of 15 degrees. So that's 400 plus 859 times sine of 21.87. So 119.98 would do. Okay. Yep, that seems reasonable. All right, so n is going to be the square root of nx squared plus ny squared. So 856.96 squared plus 719.98 squared. Take the square root. This is not coming out quite what I expected. Let me see, which part is likely it? So 859, perfectly reasonable, times cosine of 15. Oops, that's what I did. I didn't use cosine 15. I used cosine of 21.87. This is theta. Theta is 15 degrees. So, fixing this. This is 829.73. Let me check the other one and make sure I didn't make the same mistake twice. 400 plus 859 times sine of 15. Yep, I made the same mistake both places. So 622.32. All right, so we'll square that value. Plus 829.73 squared. Take the square root. There we go. 1037 newtons. Basically 1040 newtons. All right, direction. Let me change the color back because I'm no longer correcting an error. We'll take the inverse tangent of ny over nx. So 622.32 divided by 829.73 0.73 inverse tangent, and we get 36.87 degrees, or about 36.9 degrees. Okay. Now, relative to where? So if we're thinking about it, here's the contact point, here's the horizontal line. We're actually going to come up, it's a reference angle, so it's 36.9 degrees here. So N is up and to the left. So this is 36.9 degrees relative to straight to the left. Come up 36.9 degrees. Okay, I knew this would be a long one. It took 16 minutes to get through, but it's done. I'll get it posted and enjoy. Fourth example problem for statics.